So we learned about minor losses in the last class, okay, and we said minor losses would come into the picture whenever you have additional fittings in a pipe. So we said it could be sudden expansions, contractions, or gradual expansions, contractions, valves, elbows, turns, bends. Any of them could give rise to additional frictional losses, and that could be huge. And we need a way of characterizing it. And we said we were talking about loss coefficient. Okay, now typically calculation of loss coefficient is pretty difficult, and you need to depend on literature, okay, or published data to figure out what is the loss coefficient that's useful for you. Except for sudden expansion, there exists a nice calculation. So I think it's a good idea that we just look at it to get a feel of what it means. It also might give you a little more insight into the definition of loss coefficient. So what we are going to do today is to first look at frictional losses in a sudden expansion. So what we have in mind is fluid entering through a small pipe and then exiting through a large pipe. So that's a fluid streamline at the center. Others, as we said, would expand as it go along. Okay, so that's what the streamlines are going to look like. Let's say this fluid that's entering, let's say the fluid that's entering, okay, has a velocity VA, and it's exiting with a velocity, let's say VB, where V and VB are the average velocity. And let's say this cross section, the cross sectional area is SA, and the leaving cross sectional area is SB. And let's say the pressure with which it's entering is PA, and the pressure with which it is leaving is PB. And we want to calculate what might be the losses associated with it. What I'm going to do is so dealing with differential equations in this case is not going to be useful because you can't do any simplifications, okay. The flow is very complicated, so we can do an integral approach. So that's what we will do. Let's say we'll take small section. Very close to the wall and developed part. So let's call it, let's say, section A prime, and B prime. So I am basically looking at a control volume which is between A prime and B prime, and I'm going to write down a force balance and an energy balance for that region. Okay. So first is the force balance. So you have a fluid entering at some pressure, fluid is leaving at some other pressure. So there is definitely going to be some forces that might come from pressure. You could have shear stress, the wall shear stress that's acting. So that's something that you should consider. And then the fluid is changing its momentum because its velocity is changed, right? So these are the three relevant things. What we are going to do is we are going to neglect the contribution that's coming from wall shear stress. Okay, that's an approximation. We assume that wall or the viscous contribution from the wall is irrelevant in the force balance. Okay, then I can find out what is the net force acting on this fluid. That's only going to come from the pressure forces. The pressure that's acting on the left hand side, let's say, is so we know the pressure in the pressure of the incoming stream is PA. We do not know the pressure here, which is very near the wall. Let me just call it P prime. Okay, then the force that's acting along x direction is PA times SA plus P prime times SB minus SA. Okay, so that's a force acting along x direction minus the force at the section BB prime PB into SB. That's okay. I'm just multiplying pressure with area to get my force, is equal to change in the momentum, which is going to be, let's say, some mass flow rate m dot into VB minus VA. So I have said the rate of change of momentum, okay, which is I have written on the right hand side, is equal to the total forces acting in that control volume, where I have neglected the force that will come from the wall region. Okay, and I am doing that assuming that that contribution is going to be small, other losses are going to be large, and also I know that tau W, okay, the contribution that will come from the wall is really over a small section. Okay, so that is not going to be very large compared to other losses. So that's the assumption that's gone in. That's okay. So m dot is the mass flow rate. Energy. Okay, I'll simply use our energy flow equation, which again you have seen. I'll apply it between section A prime and B prime. So I'll say P A by rho G plus half V A square plus Z A is equal to P B by rho G. That's a G, no? G Z, yeah. P B by rho G plus half V B square plus G ZB plus the other losses, which is what we want to calculate. It's just applying between section A prime and BB prime. Did I miss something? Huh. Yes. So you have the fluid that's coming, it's expanding and going. So there is a force that's going to come from that section that is neglected. Yeah. Should be P by rho. So P by rho plus half V square, is it? Okay. Is this correct now? Ah. Wait, it can't be correct, no, because this is V square, so that's meter square per second square, so it should be G is Z. That sounds correct. Oh, okay. So wait, let me just check what should be then. Right, so it should be PA by rho G plus V square by 2G plus Z is equal to PB by rho G plus G. This is this okay now? Okay. Yeah. So we are looking at the total force, right, exerted in the flow direction. So it's just pressure times area. So you have this is coming from that part, okay, and this is coming from this part. Pressure on the wall. So one way to argue is that I'm going to look at a section which is very near to the wall, but why would pressure on the wall be 0? No. So that's you're blindly applying your Bernoulli's equation. But no, why should still it be 0? It need not be 0. So let me give you a counter example. Let's say you take a fluid, okay, just static fluid there, right? What would be the pressure on any side of the wall? Okay, so there is nothing like pressure should be 0 on the wall. Eh? Top meaning this region. Again. Ha. Oh, so in the static case, you mean here. So even if the pressure here is 0, okay, you have a hydrostatic pressure that will arise, right, which will act on all sides of the wall, right, and that pressure will continue to increase. So the pressure need not be 0, it's completely independent of whether the fluid is moving, not moving, anything, okay. So the pressure could be some quantity. Okay, so the forces that are acting on a solid surface need not be just viscous, it could be pressure force also. I haven't made any assumption yet, but the derivation that we are going to see, you would see that it would hold better for a turbulent flow than laminar flow, which I'll argue later. Which one? So I have a HF now. So you can say that it's just a so see P, V, everything is an average quantity here, okay. So it's just writing down what is the net energy in is equal to net energy out plus extra force, extra losses. That's okay. Yeah. Yes. Yes. No, HF is not. So there can be additional losses as we said in last time. So the velocity magnitude is changing, the velocity direction is changing, both of them will contribute to additional losses, plus there will be recirculations that will happen at the corner which will also contribute. So what HF will give you is, you know, the sum of all those things. Yeah. Okay, so the only thing is to just, okay, so we will throw away ZA, ZB because we are not going to worry about the change in elevation. So let's simplify. Okay, so there comes the second assumption, okay. Now we assume the, about something about the wall shear stress. The second assumption is that we don't know what is P prime, okay. And I am going to claim that P prime is going to be approximately equal to PA, that is the inlet pressure. Now if you ask me why do we do that, we really do not know, but if you do experiments you find that it's very close by, and the results that you are going to get from this calculation also seem to be validating this assumption, okay. So that's the second assumption that is going in. So therefore, I can simplify our pressure balance. So that's PA SA plus P prime into SB minus SA minus PB SB is equal to M dot into VB minus VA. So if I substitute P prime is equal to PA, PASA plus PASB minus PASA minus so this is PASB minus PBSB, correct, is equal to m dot. M dot is the mass flow rate. M dot is either rho VASA or is also equal to rho VBSB, mass flow rate. Okay, volumetric flow rate into density. So I'll substitute rho VBSB into VB minus VA. PA minus PB into SB is equal to rho VB SB into VB minus VA, or PA minus PB is equal to rho VB into VB minus VA. I just simplified the force balance. So now I'm gonna look at our energy balance. Okay, simplifying that, PA by rho G plus VA square by 2G is equal to PB by rho G plus VB square by 2G plus HF. Just try substituting PA minus PB and simplify and see what do you get for HF. I'm going to write this as VA minus VB because VA is going to be the larger velocity. VA minus VB whole square divided by 2G is equal to VA square by 2G into 1 minus VB by VA whole square, 1 minus VB by VA square. But we do know that VASA is VBSB. So therefore, VA square by 2G into 1 minus VB, so that's SA by SB square. So what would be our loss coefficient therefore? KE will be equal to so that's the expansion loss coefficient. And seems to be working fine. So the assumptions that we might have made should be okay. Okay. This equation is has a name. Yeah. So, so this is one of the very rare ones. Okay, in any of the other cases, as I said, you may have to just take the values from other places. But for expansion loss coefficient, this equation should work.